Hello to everyone. I'm very happy to be here with you. And I would like first of all to thank the organizers for this very exciting 2 days meeting. And today I will talk about a new biomarker for Dodecyl Creatine Ester Therapeutic Efficacy monitoring. I would like to thank all the people involved in this project, and particularly Matthew Skelton. I think that he is here. And Thomas Judino and Henri Banesh and all bioinformatic staff, Dr. Rifa Moody and Nicolas Tournier for PET imaging. I think that we are all aware on the main causes of creatine transporter deficiency, which is due to the unfunctional creatine transporter due to the mutation in creatine transporter gene. The lack of creatine into the cells, and particularly in the brain, leads to several clinical features in CTD patients, such as behavior disorder, seizure, intellectual disability, speech delay, digestive problems, hypotonia, and movement disorders. So the key question is how to improve the neurodevelopmental outcomes for CTD patients. Our driven hypothesis is to design a creatine prodrug, creatine Dodecyl Ester or CBT101, a very lipophilic compound which could cross the membrane passively without interaction with creatine transporter, to circumvent the blood-brain barrier thanks to a dedicated formulation to deliver CBT101 in the deep brain structure. And as said my colleague Thomas yesterday, by so doing, we ensure entry of CBT101 into the neuron regardless of creatine transporter activity. Based on Lipinski rule, we synthesize a library of ester creatine, and I think that you all know Lipinski rule: the molecular weight, the polar surface area, the hydrogen donor acceptor, and so on. And we design a creatine analog, and we selected the best one based on its chemical properties, which is Dodecyl Creatine Ester. When cultured fibroblasts from CTD patients with this compound, we demonstrated a significant increase in creatine in CTD patient fibroblasts, showing that DCE is converted into creatine in the cells. The administration of CBT101 in cow mice for 15 days or 1 month increase brain creatine level in different brain regions, such as hippocampus, striatum, and cortex and cerebellum. We also demonstrated the improvement of cognitive performance, as well as the modulation of proteins related to cognitive function. This suggests that a profound alteration of the molecular landscape in the brain of CTD patients could be recovered with DCE treatment. Ceres Brain Therapeutic has achieved a pharmaceutical formulation which could be administered to CTD patients. A short safety study in healthy volunteers will be conducted very shortly. And we think that any restoration of cognitive dysfunction in DCE-treated patients could take several weeks to months to manifest. Therefore, what is needed is a reliable biochemical and molecular biomarker for monitoring DCE treatments. As said former President Abraham Lincoln, the best way to predict the future is to create it. In other words, I would like to say, the best way to predict the best clinical trial is to create it by filling the gap between the in vitro, by filling the gap with the in vitro cell model based on human brain organoid from iPSC-CTD patients, and between the preclinical model and the therapeutic efficacy in clinical trial phase 2. It is well recognized that the cow model here is a high fidelity model for behavior testing. But the translation from mouse to man is a major problem that plagues biomedical sciences. So testing DCE in CTD human brain organoids provides a platform that better modeling the response of human brain. The use of both model, cow mice, and brain organoid model will strengthen the weakness of each model alone. So by so doing, we could correlate biomarker for cow mice from brain organoids and correlate with systemic biomarkers from CTD patient and for monitoring DCE efficacy treatment. The development of human brain in vivo the comparison between the development of human brain in vivo and the procedure we have used here to obtain brain organoids are very similar in terms of cell composition, in terms of the presence of synaptic markers, in terms of the vesicle structure here. What we have obtained after 2 months of cell culture, we have here the different cell type. We have the mature neuron, which express MAP2 or NEN. We have the mature neuron expressing the postsynaptic density proteins, and we have also some progenitor cells which express SOX2 as well as TBR1, which is the intermediate neuron. And we have also in this brain organoid some cells like astrocytes here expressing GFAP as well as oligodendrocytes. And very recently, we complexified this model by introducing the blood-brain barrier. Here you can see a picture. You can see here the brain capillaries around the cerebral organoid, and this brain capillaries expressing CD41, which is one of the key markers of brain endothelial cells, expressing efflux transporter like breast cancer resistance proteins. So let's talk on biomarker identification. Using this model, a mouse model of creatine transporter from Laura Barocelli, we discover in brain of cow mice more than 5,000 proteins regulated by the reduction of creatine level into the brain. And bioinformatic analysis evidenced the presence of one of the targets here, which is GSK3 beta. We observed an overexpression of this protein, and the activation of this protein dysregulates protein kinase AMPK activity and cellular trafficking of glucose receptor at the level of membrane. So by so doing, we could expect to have alteration of brain glucose metabolism in CTD pathophysiology. So what we did is to figure out this brain metabolism in cow mice. Here we have here white type animal, and here cow mice, brain imaging using fluorodeoxyglucose. And what we observe here, we have the quantification of brain activity in the different brain area. So you can see that PET imaging reveals a significant lower uptake of FDG in cow mice in comparison to the wild type animal and in several brain regions. The uptake of glucose decreased over 1 month in untreated cow mice. This is the baseline. But for longitudinal analysis, when comparing this baseline, the brain activity, and the brain activity after 1 month of DCE treatment, we could observe here by the reconstitution of the different brain regions that DCE treatment significantly mitigate the decline of glucose metabolism. We were interested by the relationship between GSK3 beta and protein kinase AMPK here, and we performed Western blot analysis in brain from CTD cow mice. As you can see, AMPK, you have 2 subunits, alpha 1 and alpha 2. And this subunit is really involved in the glucose trafficking at the cell membrane level. So what we observe is the decrease of activation of AMPK alpha 2. So the lack of AMPK, so we demonstrate the lack of AMPK activation in the brain in CTD of CTD cow mice. So using our model, brain organoid from CTD patients. So we have 3 patients here, 3, 9, and 10 years old with different clinical features. And what we observed using this brain organoid is the reduction of this kinase alpha-2 involved in glucose transporter expression at the membrane level. To summarize, we believe that the impairment of brain glucose metabolism in CTD pathophysiology could be used as a potential biomarker for monitoring drug efficacy of drug candidate, and particularly CBT101 under development by Ester Therapeutics. We could also conclude that this model, the brain organoids, could be a translational tool to study CTD pathophysiology. We were interested also on the epigenetic alteration in creatine transporter deficiency. And what is well known is that methylation of nucleic acid is one of several epigenetic mechanisms that cells can use to control gene expression. DNA methylation is crucial for normal brain development and functioning. So our driving hypothesis is that CTD cells could stimulate creatine neosynthesis to respond to the lack of creatine. By so doing, we increase the consumption of SAM here and leading to the methyl imbalance and impact on global DNA methylation. So we would like to figure out this methylation status in CTD context. So here the result we have obtained using cow mice, and here you have the 5-methylcytosine percentage of control, wild type animals, cow mice, and the mice treated by nasal administration of CBT101. You can see here an hypomethylation of DNA in cow mice, which is restored partially by our compound CBT101. We would like to confirm this result using brain organoid from CTD patients. So here our 3 patients. We generated brain organoid. Here you have methylation on DNA, 5-methylcytosine, here on RNA. What we observe is a dramatic hypomethylation of DNA methylation as well as RNA methylation. So we think that additional studies are needed to give more detail on the correspondence between peripheral blood and brain tissue across DNA domain in order to provide a context for evaluating blood-based biomarker. Let's come back to our GSK3 beta, the major target we have identified in brain cortex of cow mice. We observe also that this overactivation induces the overexpression of microtubule-associated protein. So we have a dramatic increase in the expression of this protein. And the impairment of microtubule-associated protein leads to impairment of cognitive function. And one of the protein links to microtubule-associated protein is the tau protein. So we would like to figure out if this protein could be used as also a potential biomarker. So we investigate the expression of this protein in cow mice as well as in CTD brain organoid. What we observe is that in cow mice, in brain cortex of CTD mice, cow mice, we have an increase of tau protein here, and we observe the same thing using brain organoid for CTD patient and overexpression by comparison to the LC brain organoid for LC volunteer. So our data are in agreement with the recent finding showing the elevated amyloid beta peptide and tau protein in CSF from CTD patients. So this protein could be used as a potential biomarker for monitoring CTD treatment. So the studies are ongoing. We are performing some study. We're using CTD brain organoid rescue, and we very shortly we will obtain data on the impact of CBT101 on the expression of tau protein. And thanks to the collaboration with Dr. Curie here, we expect to get plasma from CTD patient and try to correlate this protein in brain organoid, cow mice, and in plasma from CTD patient. By so doing, we could demonstrate that this biomarker, this tau protein, could be the relevant biomarker for monitoring CBT101 drug efficacy. To conclude, we believe that this tool, CTD brain organoid, is really very interesting for monitoring drug efficacy testing in vitro. And the appearance of protein changes in CTD human brain organoid will provide hints from the identification of new biomarkers that could be detected in cow mice and then cross-checked with clinical data. Thank you for attending, and I would like also, I have a special thanks for patients and families. I would like just to say one word, that you are not alone. We are working together to find the path and change the life of patients and families. Thank you for your attention.
Thank you, Aloïse. That was very interesting. Does anyone have any questions? Yes. I'll take the
Thanks so much. I'm finding that having had given up on biology in grade 12 is really hurting me this weekend, and stats in stats in first year. But what I'm curious about is there any concern for CTD patients who typically have behavior issues of increasing the level of energy in the brain is just going to lead to more aggressive behavior issues?
It's big questions. Yeah. Yes, we think that bring energy in CTD patients and more particularly increase the level of ATP by giving CPT101, increase creatine and phosphocreatine, and then you will have energy, could really improve the cognitive function in CTD patients. So, and as we show for glucose metabolism, you could modify this glucose consumption metabolism. So I think that it could really help. Yes.
Hey, Aloïse, I just have two separate questions, hopefully quick and easy. The first one is, do you anticipate there to be improved cognition? I think you mentioned that towards the beginning of your presentation, regardless of age when the CPT 101 is started. So like, would you expect to see more improvement in younger versus older? Do you expect that to matter? And then the other one is related to the end of your presentation. In order to use the tau as a biomarker, would that indicate that there would need to be a spinal tap every single measurement, or so?
Yes, I think that as soon as you will give a drug to the childhood, and better you will have a better response. So this is what we are thinking, but we need to demonstrate this fact. So the other question was?
As far as using the tau, I think that measuring the tau was the biomarker you were mentioning. Would there need to be a spinal tap every single time, or is there another way to measure that?
Okay, I think that we need. It's a good question. We need to figure out the timeline of expression of tau protein in brain organoid, and such studies need to be done. What we have demonstrated that here the brain organoid, it's 2 months brain organoid. We have also brain organoid for 4 months or 8 months, and we have this high expression of tau protein in this brain organoid for different ages. So so we need to push to continue the study, and also to figure out not only the expression of tau protein, but also the expression of phosphorylated protein, and make a ratio between phosphorylated tau protein and total tau protein. So,
Aloïse, just to follow up on that, would you be measuring it in CSF or plasma? Presumably, we can't access.
Okay, the study performed by our colleague here, it was on CSF. Okay, they measure amyloid A-beta 42, one of a key biomarker for Alzheimer's disease, and they measure total tau protein in CSF. I don't think that at Lyon Hospital the CSF was collected. We have in our biobank just plasma from 24 CTD patients, and we will figure out in this blood, in the plasma, the level of this protein and maybe the others protein.
Hi, I have a question. I'm just right in front of you here.
Oh.
Hi. Thanks so much for coming out and speaking to this. It sounds like you've been working with CTD in some form or fashion for a long time, and
Yes.
that really means a lot.
10 years ago.
Yes, so thank you so much. It's so cool to be here and to hear all this. But my question was around, you were speaking, which I haven't heard a lot about like the glucose levels in the brain. And I'm just curious if you think that administering the CBT 101 would have any impact to the overall blood glucose levels of the patient that we would have to maybe monitor as well.
Good question. I think that this this need to be figured out, and we have no answer right now. What we observe is the only partial restoration into the brain. This is a good thing, you know, to increase metabolism and energy for brain functioning. And but yes, we need to figure out the level of glucose in the body. Yes.
Are you saying that the levels for patients with CTD are lower? Sorry.
Sorry.
It just came into my mind.
In CTD patients?
Yeah, as far as like the glucose levels in the brain, are those lower or are those?
I think that this is just my feeling. Okay, we observe this overexpression of GSK3 beta. This protein, this kinase, regulates glucose transporter at the level of membrane. And I assume that in CTD patients, we could observe the same things. So an hypo glucose metabolism in CTD patients. And this is what I'm thinking, due to our findings and what we expect. We expect that when we will give our drug, CBT 101, to patients, we will increase brain activity.
Would you think that a helpful measure for safety for these patients would be to monitor their blood glucose levels through like a BGM device? If you feel like at a specific time points, just to ensure that they're not dropping into some type of hypoglycemia or anything like that?
We need to check.
Okay.
Yes.
Hi, thanks for your talk. I think it's really interesting to see the brain organoids used for all of this, and this, of course, looks at the brain. I was wondering if you're also planning to use muscle cultures to look at the effects in muscle cells? No, it's we are not involved in such project, but it will be, yes, nice to check in muscle what happening. But yes, of course.
Hi, thank you. It's really good to know that there are potential biomarkers that can be used in clinical trials. I'm just curious about the feasibility of these biomarkers, because following up with Celeste's question, glucose is measured by imaging, right? So we will need to sedate kits to measure that, or for the second one, I didn't quite catch it, but it looks like you used Western blot, so you will probably need some tissues to measure that, and for tau it'll be spinal tap. So I was just wondering the feasibility of these biomarkers if you have to follow these kits for a while, as a parent, I don't want to put my kid down every time for imaging. So I wanted to know more about that.
Very interesting question. So PET imaging is currently used for epilepsy, for example. from monitoring brain activity and in post-operatoire. It's PET imaging is used in Parkinson's disease already. So it's a relevant tool currently used in children and in adults. So I think that assessing brain glucose metabolism in CTD patient is feasible. The biomarker we have identified in plasma, it's non-invasive. So you could just take blood from patients and measure using ELISA, for example, the amount of tau protein in blood circulation. So it's non-invasive. So I think that both approaches are really interesting for monitoring drug efficacy in CTD patients. So it's not Western blot. The Western blot just was to try to correlate the expression of our GSK3 beta, our target protein, and one of the kinases involved in trafficking of glucose receptor at the cell membrane. It's just understanding the molecular mechanism. But for the monitoring of drug efficacy testing, blood samples, PET imaging, already and currently used in clinics. Sorry.
Hi, I've got a question, actually kind of two questions over here. So when you had talked about the hypomethylation and being able to possibly add SAM, more or less, was that ever followed up to see if the addition of excess SAM for that enzymatic activity would, I don't know, kick anything out on the end to give you a different biomarker that you can monitor? Number one there. And then number two, it's interesting with the, I don't know every protein, but the PLC, that's usually involved for PLC beta with GPCR signaling. So those can be monitored probably more easily than like CFS, samples and stuff like that from calcium, like uptake assays and stuff. So have you followed up on the PLC beta side to see essentially the additional signaling that it is activating?
Yes, you're right. I just pointed out the expression of tau protein. This is one of protein, but what we have discovered 5,000 protein in brain cortex of cow mice regulated by the reduction of creatine to the brain. And one of the other protein, the biomarker we have identified is KIF1A and PLCP1. So we have a list of protein we will like to monitor in plasma. I don't know if we could find this protein in plasma. Maybe. I don't know if this protein could move to the plasma through the CSF, the cerebrospinal fluid, or through the extracellular vesicles released by the brain endothelial cells. So we need to check those additional biomarkers. I think that it's very important to have a list of biomarkers for confidence and in terms of DC-CBT101 efficacy treatment. So you're right.
Thank you.
Thank you. Any more questions? Okay. Thank you very much.
You're welcome.